Hello everybody. Today is August 21st, 2018, and I'm going to go back to another August date, very important marker for me, with 4x4 parity algorithms, and that is on August 2nd, 2010 I uploaded this video. I think I might have renamed it different things, but this is the final name I came up with for it. This is what I call the Holy Grail algorithm. Even though it's really not the Holy Grail, there's another algorithm that I later found that is just as significant as it and also shorter in one move metric. And a lot of the terms I am going to talk about in this video and some prerequisite knowledge that you should know if you are new to parity algorithm theory, you haven't followed my work, is to take a look at the introduction of the 4x4 parity algorithms page at Speed Solving Wiki, which I've written. And so therefore I don't feel the need to actually explain any of that in this video. But if you followed my work by at least watching some of these videos in the past, maybe at least like derivation of the Holy Grail algorithm parts 1 and 2, parts 3 and 4 aren't really necessary for this video because this talk is not going to be about translating these algorithms to larger cubes. It's just about algorithms for the 4x4 mainly, not even the 5x5. But there are some things in the second part of this derivation series which I'm going to show soon for a refresher. So if you followed my work from seeing videos in this playlist, or if you've seen the thread that I've started at speedsolving.com, which is entitled Methods of Forming Two-Cycle Odd Parity Algorithms for Big Cubes, and there I introduced the Holy Grail after I derived the standard algorithm. Seems like a lot of people liked at least the first and second, maybe the first part. People had a lot of likes for that video and I appreciate that. Not so much likes for the other ones, but I guess because they're pretty much the same thing. But this was my first presentation of the Holy Grail algorithm. But I haven't made a video about it, but in 2016 I found an 18 quarter turn algorithm, shorter than the Holy Grail, for the 4x4. It only works on the 4x4. If we go to the 4x4 parity algorithms page at Speed Solving Wiki, I strongly encourage you to read the introduction. Not so much names and labels, but I would say everything else. Names and labels is not really necessary. Just scroll down. This is what this video is going to be about. Just let me briefly just show this. This seems to be a very popular algorithm these days. This is an algorithm by Friedrich Beatty. I believe he treated the 4x4 like domino. That's how most people have done it, and then they've solved this, but I'm not sure. But however he found it, that's fine. What matters is he found it pretty early, in the late 90s, if not earlier. I'm not quite sure. But basically this is what this looks like. I've seen tutorials like this. I've seen tutorials on that on all over YouTube recently. But people might, if they don't know that 15 move algorithm, then they probably know this one. This is called the Red Bull by some people. I don't know why. But this is an algorithm I have a derivation for. Now, compare those algorithms, the way they look with execution, to this. This is the 18 quarter turn algorithm I found in 2016. It was early 2016, January, but just take a look at the differences. Should be quite obvious. The other algorithms, if you would take a look at them in their notation, whenever you see a 2, you count that twice. Each of those to me is 2 moves, like F2 is 2 moves, not 1. But that's just in this move metric. I can completely understand that F2 in the half turn metric is 1 move. It is the shortest in this list. I have them arranged by shortest and half turns in this list, so 17 is the shortest technically, but that's for that metric. But for quarter turn, 18 is the shortest. And just to give you a brief history on when I lowered the upper bound for this move metric for the single edge flip case. I asked Chris Hardwick on the speed solving forums in 2009 when I joined about this, and he was saying that he got the Red Bull algorithm. He didn't say Red Bull, but some of you know that as Red Bull. He got that in 1998. I don't exactly remember from which site, but it's been around for a while. And then in 2009, clearly you can see the dates. Now remember when I announced on the forums that I found a 24 quarter turn algorithm, some members were convinced that I didn't know how to count my moves, and that was kind of funny. And I guess I didn't blame them because I didn't show any of my algorithms until later. But briefly, if we go here, the first wide turn based algorithm that I showed was the Holy Grail algorithm, and that was in this thread, the methods for forming two-cycle odd parity algorithms for big cubes. And I showed that on this date, August 2nd, 2010. But if we go back here, I was announcing in the forums each and every time I lowered the upper bound, but I didn't show it. And there was a big gap from when I found the 19 to when I actually showed and proved that I found them. But then there's this huge gap from 2010 to 2016 when I find the 18. That made me wonder. I was like, now that I found that, will there be another huge gap in which I will find the 17 quarter turn algorithm for the single edge flip? And now, despite that these algorithms and the algorithms that you may have been aware of in the past that I have for other two-cycle cases, which I'll get to shortly, are so brief, and despite that they look impressive, I have recently uncovered the full truth behind them and their nature, to the extent that I found it feasible to find all possible wide turn based two-cycle parity algorithms from any given base two-cycle algorithm. Now, what I mean by base two-cycle algorithm is, well, for those who haven't watched part 2 of the derivation of the Holy Grail algorithm video in this playlist, here's a quick minute portion of that 8-year-old video which pretty much explains what I mean. One quick thing to note about how this almost looks like an interior J-perm. If we take a look at this and we compare it, if you've watched the derivation of the standard algorithm or with other algorithms which are single slice turn based, not wide turn based like this one, you can visualize this as being an interior J-perm slid toward us, because this is the front, so it's slid toward us one piece. For example, this is the interior J-perm which is seen from normal algorithms. This is what you need to build a pure edge flip algorithm from them. And all that we have is the same amount of pieces. The only thing is, whoop, it's moved. You see? So that's why we can still make a pure algorithm from this, and it can be as brief as it can be, because we still affect the same amount of pieces, just in a different way, so we have to handle it differently. So obviously, what I've done, if those who haven't figured it out by now, is I figured out a way to program this. It's not brute force entirely, because I technically have not done a computer search to search for every possible base that there is that could potentially yield short algorithms from. And a better word for it is not base. We'll see soon. It should be called seed. I can briefly show them here. This is just some markers that I had for me when I was running my program. This is basically a 3-cycle of 1x2x2 blocks. So if I just copy this, and once you have this, and I can briefly show how to make this, I use old WCA notation, just as I do on the wiki, but the links are with signs, so I apologize for that. But there just really isn't, if you were wondering, there really isn't a online simulator or applet which uses old WCA notation. And I'm talking about like where a lowercase letter means an inner slice, not 2R means inner slice R. I'm not against that notation, it's just a different notation what I'm going to use in this video and what I use in my program. I use this one with W meaning wide and lowercase letters meaning inner slice. But basically, if we do these three moves, LW, FW prime, L prime, that's the X in the commutator XY. So basically, if we look at this slice here, the back slice, look at that, it's all solved except for this 1x2x2 block. If I would do a, say, B prime move here, that is the Y in the commutator XY. And now I will undo that portion. So let me write it like this. So this is x, this is y, this is x inverse, and then this is y inverse. When I do that, then I have a 3 cycle of the pieces that were isolated in that slice, which I term with y. This is called a piece isolating commutator. And now if I just do a cyclic shift of this, of 4 moves, then I will get the same 3 cycle of 1x2x2 blocks that I had previously. On the 4x4 parity algorithms page, if I go to it, let me just show you to read a little bit about that. It's at the beginning here, in this section, right under pure flips. For shortest half-turn algorithms, I talk about cyclic shifting here. So you can go ahead and read that. And the idea is this. Once you have this, just try to move all of these into one slice. And I don't have to do setup moves to this like I did in my previous videos. I've learned that another way to do it, and it might be easier, is just try to visualize. Let me just go to the numbered cube. That's easier for me to visualize. I have this special numbered cube that I made in Cube Twister to help me out. I have 3 wing edges here, 17, 2, and 20. Since this is a B move, I'm going to also use a B move, so there might be a move cancellation or at least a move merge. So I can do maybe a like B2 move or something. And then I can do a, say, DW. Then that will get these 3 in the same slice. All I have to do now is just a quarter turn. I may have done it in the wrong direction. I really don't need to memorize this. I mean, you can just eyeball it. If it's a 4 cycle, I went in the wrong direction, and I did. No problem. Just invert the quarter turn, and then you will get a 2 cycle. This is a base, what I call a base, but this is actually a seed. Because from this seed, you can literally, with my program, make thousands of algorithms for every possible 2 cycle case that can manifest on a 4x4. And how that works is, if I write this, or I say just make it all in one line, I do not cancel moves with the 3 cycle of 1x2x2 blocks and the 4 cycle conjugate. What I do is I just put an extra space there. As I've shown here in this text file, I have the 3 cycle and then I have the 4 cycle. Collectively they make a 2 cycle, which will discolor either 2 or 4 X centers. X centers are just these centers here because X. But basically from this point, I guess I'll go ahead and explain the method, is I temporarily erase the 4 cycle. So I write it 3 cycle, 4 cycle. What I'll do from that point is temporarily remove the 4 cycle, and I will observe which pieces the 3 cycle affects. Now I'm going to paste the 4 cycle and I'm going to temporarily erase the 3 cycle. This is the 4 cycle. It will affect more because it's a 4 cycle, not a 3. It also affects this down here. This is another piece. So basically what the method says is the pieces which are not at their intersection, at the intersection of the 4 cycle and 3 cycle, it is in those faces or slices in which I can do some interior setup moves or setup moves in between these 2 algorithm pieces to affect different edges or centers, and that the overall combination of the 3 cycle and 4 cycle, or the seed, will affect. So in this case, these 2 pieces here are not at the intersection of the 4 cycle and 3 cycle. Again, briefly, this is the 4 cycle. I'm going to show the 3 cycle again. You can see here that it's just these. There's no other pieces on the cube anywhere. So again, observe the 4 cycle. So the B face, capital B. That face we're going to be allowed to turn, and it's going to keep the 2 cycle. It's going to maintain it, but it's going to be able to change what pieces this 2 cycle seed affects. Also, in the bottom here, we can move the D face because this piece here is affected by the 4 cycle but not the 3 cycle. And you just see what pieces one affects that the other doesn't. And if it happens that those pieces are isolated in a face, that you can turn that face without affecting the pieces that they do intersect with. In this case, the face B, I can turn B without affecting anything that the 3 cycle affects, which again is here. Turning B is not going to affect any of these pieces. and turning D will not affect anything that this 3-cycle affects. So therefore, let me just go ahead and this is the 2-cycle base or seed as a whole. Now that we know which slices we're allowed to do, let me just do a B move here and let me undo it here. If I do that, then I still have a 2-cycle of wings and a 2-2 cycle of X centers. But look at it, it's different. And take a look here. This is a B prime and this is a B2. Those merge to a lowercase b, and that can merge with this B to become BW. So all this can merge to become one move. And this capital B here can merge with this B2 here to become 2 block quarter turns instead of 3 as it's currently presented. So it is by this logic combined with, hey, let me now take this base that has an interior setup move in it and let me conjugate it to try to make a 2-cycle algorithm. Well, let me just do like, well, this is not going to be a dead flip, but let me just do this. That's going to take care of those 2 X centers there, and well, if I want to not discolor this one with this one, let me just do like a B and then B prime, so that this is in line with this, so that with this move, and I undo that move, then I have an algorithm for this 2-cycle case. And I guess that brings me to the topic of the other last layer 2-cycle cases. At the very beginning in the introduction of the page, I mentioned this case here. This is one of them. But we're going to take a look at the rest. Okay, so here's that case. The shortest algorithm for this in this block quarter turn metric turns out to be 16 quarter turns and 15 half turns. And it turns out that the 18 quarter turn algorithm that I found, there's only one of them. It is unique, according to my search. Same holds true for this case. The 1615 is the only one. It is the only one. I found algorithms that are wide turn equivalent to this, but it is the only one. On the other hand, if we go to diagonal, I have two 1615s, so 16 quarter turns, and I also have a 1616 as well. So I have 3 16 move algorithms there, and let's see if I have some down here. And I have a 16 move algorithm down here as well. Now what is the difference between this 16 move algorithm? Like, why did I separate it from this 16 move algorithm here, the 1616s? Why are they separate? Well, here it is, symmetrical, non-symmetrical. So if you've seen the wiki page, you know the difference between them, what I define as symmetrical versus non-symmetrical. If you don't, I define it up here in the 15 move section. But go here, additional terminology, symmetrical, non-symmetrical. So I explain what that means there. So for the diagonal case, we have both symmetrical and non-symmetrical, that they're both 16 quarter turns, and that is the absolute minimum that appears to be achievable with this method. So that was the second one, the diagonal. Then I have what I call close unoriented, and then the next case is far unoriented, and then I have oriented. So that's the algorithm that I found here. This is just a mirror of that case. So with my search, I found algorithms for all of these cases, every possible algorithm from all of these seeds. So coming back to this section of the wiki, and also mentioning again that this is the only 18 quarter turn algorithm that I found in my search, and actually Ben Whitmore, who I've had a nice conversation with via email, and of which I think he would not mind me sharing with everyone. I made a PDF, Microsoft Word, just nothing too fancy, but I kind of made it look like a forum style instead of our personal emails, of discussing whether or not this really is unique. And we really don't know. We were both searching for 17 quarter turn algorithms. I failed with my search and he didn't succeed with his. So it's possible that my 18 move algorithm is the briefest algorithm for the single Dutch flip case in this move metric, and it is the only one. But as I said, the 1615 for the opposite 2-cycle case is, I'm claiming, to be the only one for that case as well. So it's, since they're both 2-cycle cases in the last layer, this really isn't something unusual. It kind of fits the general trend, it seems like. But on the other hand, we've seen another one that had 316, so it's kind of random. But I'll go ahead and provide a link in the video description to that PDF so you can see our conversation and what observations I made about the method I just showed you with the interior and exterior conjugates. And also you can see before I added all of the new algorithms I found with my program, what algorithms I found beforehand versus the new ones that I found, and seeing how they're different. And one thing I did find with the program that I could not find by hand because I just didn't, it was a little bit unobvious, is a non-symmetrical single edge flip algorithm. It didn't find any others. Very neat. I found some non-symmetrical edge flip algorithms myself. These, if you click on this link, this was from 2012, I believe. Yes, it was February 25th, 2012, where I found these. Actually came up with a method for that in that post. So if you want to take a look at that, just find this part in the wiki. And if for some reason someone wants me to make a video about it, which would be okay, I could make a video about it explaining it in more detail in video form on how to make non-symmetrical algorithms by hand instead of, well, for this case, just to show you briefly how difficult it can be if I'm not allowed to do any exterior setup moves. None. If I just would try to insert different moves here and somehow it wouldn't discolor any X centers. And I would be allowed to, and with the method, if you're unaware, I'm also allowed to shift, cyclically shift. That means just taking the first move and making the last move. I'm allowed to do all of that and still have these and change these. So there's different parameters to take into account here. And I'm also allowed to reconjugate too for symmetrical algorithms. But just for non-symmetrical, I'm allowed to shift and I'm allowed to insert. That's all I'm allowed to do. I cannot add any on the outside. I did a search using these bases here. This is the number of algorithms it found. Now I did several software components to this. But basically I eliminated a lot of duplicates as I was finding them. So that's what the left column here is for initial. And then I wrote a separate routine after I found them all and I collected them all. Then I reduced them by some trivial things, like if you have a single edge flip algorithm, I eliminated all algorithms that began with U and ended with U, for example, because that's kind of redundant. Or algorithms which a single digit flip algorithm began with R and ended with R, things like that. I eliminated those, and basically what's left is this. So it's quite a few, isn't it? So these are the text files here. This is what they're named. I'll have it provided for you. You see, this is the reduced algorithms. If for some reason someone wants the ones that aren't reduced, when I mean that aren't reduced, the initial set, I can provide that for you as well, but they're just redundant algorithms that when you see the code, if you're a programmer, you know what I'm talking about. You know that it's not, I didn't make a mistake with it, at least hopefully not, to omit some algorithms that I found. But I'm going to give you this set right here because it's fewer megabytes. Let me just briefly say why there were so many algorithms. It's because, for example, the shortest edge flip algorithm found from the search. Let me just go here to the single edge flip algorithm. This is that list. I have 2001 of these. I labeled it symmetrical algorithms, and then at the very bottom I have, let me just scroll up this mess here, non-symmetrical algorithms. For those who see these files, note that this is the only non-symmetrical algorithm. These are actually symmetrical, but basically the routine that I went from initial to reduction just basically separated symmetrical from quote-unquote non-symmetrical by saying, is the first move displayed in the string? Is the first move equivalent to the last move? So like for this one, this is not equivalent to this, despite that this, these can be rearranged. So that's why these are here. So when you see this, not all of them are symmetrical. For the single edge flip case, I've already done the work. This is the only one that it found, the only one. But for other two-cycle cases in the last layer, there are some. There definitely are some non-symmetrical, so it's not all redundant. But if you want to manually go through and delete all of these, you're more than welcome to write a routine of your own to do that. That's fine. So what I wanted to show is the shortest algorithm is 18. And these two are equivalent by wide term equivalences. If you see up until this point right here, these two algorithms are identical. There's no debate about that. Right here they start to differ. But LW is equivalent to RW with an x cube rotation, and I talk about wide term equivalences on the wiki page in the introduction. So therefore, from between here and here, there's going to be a minor difference, but then it resumes here. So these are identical, so I only found one. And some of these 19Qs simplify down to the same 18Q. So this list here, some of them can do some simplification. It's not too much simplification, because I wrote an algorithm simplification for my software as well that wrote like this: F2 FW. For example, it reduced this. Instead of any other equivalent of it, they're all uniform. They will have that format. If it's equivalent to this, it's going to be like this. So that allowed me to eliminate a lot of duplicates before I even established the initial amount. And then from the reduction, I re-implemented that feature into that routine to go from initial to reduction, just to be sure. And I still have this large number of algorithms. Now let me briefly say this. Other is any case not confined to the last layer. I didn't sort these at all, so that's why this is a huge number. But since I was searching, I was basically finding any two-cycle algorithm which did not discolor any X centers, and I would save it and then discard the rest. And I wrote a routine to identify all of these cases except for other, and then I sorted them and separated them like that with my program. Also, a few other stats. Total search CPU time, 27 days, 6 hours, 40 minutes, and 21 seconds. I searched through every possible interior setup move, in addition to every possible exterior setup move possibility, including none of them as well, aka non-symmetrical algorithms. So if an algorithm used exterior setup moves, it would be what I call symmetrical, and if it doesn't, it's non-symmetrical. It's that simple. So the total CPU time was 27 days, 6 hours, 40 minutes, 21 seconds. The total chosen, I'll say chosen, customly chosen search space was 49,286,562. So that's how many different scenarios they went through, and that's how long it took to do it, and this is how many algorithms it found from that. So it was a smart brute force search with this specific method. So it's not really a software system that I would call a solver, even though it technically is. It's not a brute force solver, that would take too long, but it found so many algorithms with it. So with the single Dutch flip, the range of algorithm lengths, the reason why it was so many algorithms, which I'm trying to explain, the minimum was 18, and it goes all the way to 26, 24 maybe, or over here 25, 20, so 26, 24. So from 18 to 26 quarter turn move algorithms, it found all of these. My program rotated all of these algorithms so that they correspond. I know it's a lot of information, but I just really didn't know how to structure this video. But basically, like for the opposite case, all the algorithms listed in the text file, like the one I just showed for the single Dutch flip, the one for the opposite case, they're all rotated in the last layer to be exactly in this position so that you can use any one of them to solve this exact case image. So I eliminated a lot of duplicates that way also, because when you cyclically shift these algorithms, they can be in any position around the cube. But I rotated them all to be in these positions here, just like these. So that's why we have so many algorithms, because it turns out, and it should be obvious, that the longer the algorithm is, the more of them there are, considering that I was saying the 18 block quarter turn algorithm I found for the single Dutch flip and the 1615 for the opposite case, there's really only one of each of them. And there's only 3 or maybe 4 of the minimum for some of the other cases. So it's very few. Now, for those who are software programmers, total search space, 50 million. Total CPU time, a month. That seems to be very slow. I know it is. But I just programmed this 4x4 solver for the first time. not too long ago, I guess a couple years ago, and then I used it for different purposes. But then recently, when they had that conversation with Ben, which you can see those emails that I talked about earlier, that's in that single PDF, you can see the results I got from the program. But from that point until the present, because that was like in January, February, and now it's August, about 3 weeks ago I resumed this project and made a complete software system which consists of 3 notebooks. This is programmed in Mathematica, so if you want to see this or use this, if you have Mathematica, great, just go ahead and use it. If you don't have Mathematica, you can get the trial version and use it. But let me just give you an example of what it looks like, the program when it's run. So this is the software system. Let me just go by type here. There are 3 dependent notebooks. This one, and this one. This is extra for a version of this. So you need to initialize them all. Then every single module in them will work. But this is the main notebook. Let me just take like this. So now what I'm going to do here is I'm going to paste it. And this 0 here, just let me say this means that I want 0 X centers discolored. I'll briefly do 2 after I show you this. Let it run a little bit just to show you, but that means I want 0 centers discolored. So this is the 3 cycle portion, this is the 4 cycle portion. So what it's going to do is I wrote a routine to detect phases B and D, for example, for this particular combination of 4 cycle and 3 cycle to use for interior setup moves. And then I'm going to use every possible, let me go here, let me show you this. This right here is the number of, this is the main program, so the number of interior setup moves is the first parameter. Number of exterior is the second. So if I go back now, go back here, and I can clean this up if someone requested. I can clean this up. This is the combinations that I ran. I said too much memory for 4. For maybe not for interior, maybe not so, but for exterior it certainly would be. Not good. And 5, man, my computer froze when I tried to use permutations to calculate the number of permutations of taking 5 at a time out of all of the moves. With this type of base, there are actually a minimum, from what I have been able to find, of 5 quarter turns that you can do before and after this to make it a pure edge flip. That was something else. And since I'm mentioning that, let me just briefly go back to my setup moves notebook to show you the string of moves which it found the permutations of, and that's this right here. I have this also because I had a theory that maybe the L, F, and D could be avoided if you use the R, B, and U, for example, something like that. So I had this on the side here, but I decided not to use it. I decided to use the full set of, I think it's 42 members, 42 different move types, and I composed all these. This is what I took the permutations of. But taking this and counting the number of permutations it would take to 5 at a time, oh, that just froze my computer. And 4, it's quite a bit. For 3, I think it's like 68,000 something around there, maybe 70,000 different possible moves. For taking 2 at a time, it's much less, and of course taking 1 at a time is just this list right here. So it's exponential in growth, maybe even more than that. So that's why I said too much memory for this one, because it would be. Because when you multiply this by how many different possible ways you can cyclically shift the seed, that you multiply those two together, and then you also multiply the number of interior setup moves set as well to it, it would be too much. But these are all the possibilities the program's going to go through. This is the runner, or the UI. So I'm going to go ahead and run it. I have it talk for us.
Search complete.
Searching for 1 interior set of move, 0 exterior. So it's searching for non-symmetrical, and I have it say that here. So it's searching for non-symmetrical in the specified space. Search space 36, and then you can see if you look at the code later on how I calculate the search space, but it's basically doing those multiplications that I told you.
Complete. Rotating
0 algorithms
and
found.
mirroring Algs to be in
Actual
the last layer.
computation time versus what I have projected, just to save you time if you want to run this yourself and get an idea of how long it is. It's not entirely accurate, not for every case, because it's kind of random with how many algorithms it finds, because it has to simplify them and rotate them into the last layer before it displays them to the user. So it's kind of random, it's not accurate, but I have that as well. And here it didn't find any, here it didn't find any, but it will tell you. I don't know if it's gonna finish, but it shows in this case, whatever case it finds algorithms to, it's going to show it oriented, and it found 16 move algorithms. For the longer computational times, it will give you what percent done it actually is in finding the algorithms, but it won't be the percent done in actually displaying them to you. That will be a separate increment of time that it's unknown, so I didn't mention that. But this is how to use the program. That's basically it. So you just take one of these, you copy it, or if you have your own, you just put the 3 cycle in quotes, then put a comma, put the put the 4 cycle in quotes, and then just copy and paste it. Initialize all the notebooks first, then copy and paste it in here. Go all the way to the end of the notebook, right above these lines of code here, and just paste it right here. And this is 0. Now briefly, let me just show you this algorithm here. Just show you that it doesn't discolor any centers, and just briefly show it. So here it's oriented case, and as I said earlier, the program does rotate it to be in the exact position here as it is on the wiki, and you can see there are no centers discolored at all. Pretty straightforward. But let me just briefly show what's going on. It's almost finished with this computation, so maybe I'll let you just see it in action. Yeah, just a few more seconds.
Search complete. Rotating and or mirroring Algs to be in the last layer.
It is at this time that I don't know how long it's going to take to do what I just told you it does. Here we go. So that's how it works. It only found oriented for this time, but it will find, if for a given seed, if it finds algorithms for other cases, it's going to show them what their algorithms as well. And let me just briefly show this, like I was mentioning earlier. If I just replace that with a 2, then I'm going to be getting algorithms that discolor 2 X centers instead of none or 0. So if I run it,
search complete. Rotating and or mirroring Algs to be in the last layer.
See, it already found some because these are much more prevalent.
And or mirroring
so I'm just going to
be in the last
quit the evaluation just so we don't have to see that. And if I just copy this and I paste it there, we can see that these two are messed up, but they're not discolored, but these two are messed up and discolored, so it's just 2. So that's basically what this does here. This 2 tells you, and maybe you can have 4 also. I can try 4. See what happens.
Search complete. Rotating and or mirroring Algs to be in the last layer.
Wow, so you see it found a lot more of them. They're much more prevalent. If I have an oriented case, and I don't care how many X centers are discolored, in this case it will be 4 because I specified 4. Then, here we have 4. All 4 of them are discolored. And it's very, very brief, but it's pretty worthless for us. As I was saying earlier, it goes through these combinations here. So there's actually 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it will just count how many arguments are in this list. So if you comment or uncomment these, it's going to say X out of Y. In this case, there's 12 of them. So this was run 10 out of 12 with this first seed, and it took, well, the projected time was 3 hours and 1 minute, and after it executed, it found some cases for opposite. If it would have found edge flip, that's listed first, but it didn't. It found opposite though, so you can see that here, that it found opposite. not the briefest. The 1716 is not the briefest. It's 1615. That would be achieved with another base. But this is another case diagonal, so yeah, and so forth. So that's how this program works, and this is all the output. And it will go all the way to 12 of 12. And then once it's done, let me just go to the currently running notebook that that we're looking at here. It's at 50%, but I'm going to stop it right now because I have this as a global variable. So whatever it currently found, it put in here on the previous runs. So I'm going to stop it. I'm going to say abort. I'm going to go here. I'm going to select this. I'm going to press the enter or shift enter to guarantee that it will work. 0. There is no edge flip algorithms. Here 0 opposite. Here 12 diagonal. So since I have 12 of the diagonal, let me just go to diagonal here. So it puts them all into a list and it counts the number of moves of each. And that's basically when I took all of these and I went from initial to reduction with another notebook, which is not officially part of the software system. I wouldn't consider it as eliminating. So each of these shows it's just one routine here called reduce Algs, and you can see I commented it some. I think it's sufficient commenting for this. It's very self-explanatory, but I basically said which move sequences I found that I wanted to eliminate. This is the number it started with, and this is how many it ended up with for symmetrical. And then I had it separate symmetrical from non-symmetrical, which I said at the very beginning of the video. And some of the non-symmetrical aren't really non-symmetrical, but this is that program. So this is quite a bit of information. Quite a bit to take in. But if anyone has any questions about this, or this method, or the software, just please let me know in the comments. Since I began this video with a little bit of history, for example the dates when I lowered the upper bounds for the single edge flip position, if I briefly go to the shortest half turn move algorithms and I go to non-symmetrical, it took me forever to figure out wide turn based non-symmetrical algorithms. As you can see now with the software and with this method, it's pretty trivial, although cumbersome to try to do by hand to find them, especially that they're so rare. But this 19 quarter turn algorithm that I showed you previously is the only one it found. That's how rare they are. It's only one. But this one was very special for me because, and as I was just in the section of the wiki that I was starting to talk about this, is that when I saw this and I found like single edge flip algorithms like the Holy Grail and Challenger and Reverter and all of them, and I was lowering those upper bounds, I was like, is it possible that a 19 block quarter turn algorithm could exist that's non-symmetrical in structure? And just satisfying that curiosity after so many years of starting from 2009 when I first found the symmetrical algorithms that I did until February 2018. And even though there's only one 18, it makes sense that the 18 that does exist is symmetrical, because if you think about it, if we go back here to this example, if I'm allowed to do both interior, and there could be a move merge or cancellation with that in this, and exterior moves where I might have an LW prime as exterior here, and there'll be L here, which won't cancel with that, but it cancels with this, there's more room for move cancellations and move merges. It makes sense, therefore, that symmetrical would be briefer. But at the same time, if we go to the wiki, you can just see that the algorithms that I found from this computer search for the other two cycle cases, as I mentioned previously, I have 16s in the symmetrical, but then I also have some 16s in the non-symmetrical. So in a way, it's like, whoa, there's just some interesting things going on here. So in short, my search for this type of algorithm has finished. If you find a seed and you don't want to run the software, or don't know how, or don't have access to Mathematica for some reason or another, if you find a seed which is different than the ones that I've had, and it finds new algorithms, I will attribute them to your name. I will happily use my program, if you don't yourself, and run it and find all possible 2-cycle algorithms that can exist in the 4x4 cube. Should you find a 17Q edge flip algorithm or any quantity of moves equivalent to the optimal algorithms, that would be a great find and would be a great addition to the wiki. So I really encourage those out there who are interested to do such a thing.